Now let's see some important physical quantities of chapter number 4, and we'll see its units, dimensional formula, and I will give you some formulas as well. So let's see Lorentz force. Lorentz force is given by the equation F is equal to Q into bracket E plus V cross B. This actually is the force acting on a charged particle when it is moving in presence of magnetic field and electric field. If only electric field is present, then the given equation is given by F is equal to QE. If only magnetic field is present, then the equation is given by F is equal to Q into bracket V cross B. Okay, so we can say this is the magnetic force, this is the electric force. The combination of this electric and magnetic force gives the Lorentz force. This is the equation of Lorentz force. Now as this is force, its unit is Newton or dyne. So dimensional formula will be, it's just a force, so it's very simple. F is equal to m1 L1 T minus 2. Okay, let's see magnetic field. There are too many formulas for magnetic field, but the one which gives the unit very easily is F is equal to Bill. Remember, F is equal to Bill. So that's why we can say B is equal to F by IL. The unit of force is Newton, unit of I, current, is ampere, L is length, means meter. So Newton per ampere meter is the unit of magnetic field. This Newton per ampere meter is also called Tesla. So this is generally preferred. Tesla is a unit of magnetic field. So other than Tesla, Gauss is also the unit of magnetic field. 1 Gauss is a 10 raised to minus 4 Tesla. Or we can say 1 Tesla is 10 raised to 4 Gauss. This also is a unit of magnetic field. Now let's see its dimensional formula. Dimensional formula of magnetic field, very very important, is, see, the dimension formula of force is m1 L1 T minus 2. Ampere means A1, meter means L1. So we'll get m1 T minus 2 A minus 1. This is the dimensional formula of magnetic field. Let's see unit and dimensional formula for magnetic permeability. See, the formula for magnetic field is B is equal to Munni for a solenoid. Magnetic field inside a long solenoid is B is equal to Munni. Here mu 0 is called permeability, and we want to find out, mu 0 is the permeability, and we want to find out the unit and dimensional formula of magnetic permeability. So we can say mu 0 will be B by Ni. Now the unit of magnetic field is a Tesla per, see, small n is number of turns per unit length. So this is number of turns per unit length. Current means ampere. So we can say, see, this length goes in the numerator, we get Tesla meter per ampere. As number of turns has no unit, therefore we will have Tesla meter per ampere. Now let's see its dimensional formula. Dimensional formula of mu 0. See, dimensional formula of magnetic field is m1 T minus 2 A minus 1. So let m1 T minus 2 A minus 1 divided by, Tesla into meter. Meter means into L1 by A is ampere. We'll write A1. We will get m1 T minus 2, m1 L1 T minus 2 A minus 2. So once again, the unit of magnetic permeability is Tesla meter per ampere, and its dimensional formula is m1 L1 T minus 2 A minus 2. You can remember it like this. This mu 0 actually is F by I square. This is F by I square. Force means m1 L1 T minus 2. I square means A minus 2. Okay. Let's see magnetic moment. Magnetic moment is given by the formula m is equal to ENA. Remember the formula MENA. M is equal to INA. Here the unit of current is ampere. Unit of number of turns, there is no unit for number of turns. The unit of area is meter square. So ampere meter square is the unit of magnetic moment. It's a dimensional formula. Dimensional formula of magnetic moment. Sometimes it is also indicated as mu is equal to ampere means A1, length means L2. L2A1 or A1 L2 is the dimensional formula of magnetic moment. Now magnetic flux. The formula for magnetic flux is phi is equal to B dot A, sometimes written as bar cos theta, BA cos theta. If the area or magnetic field is not uniform, we can also use the formula integration bada means B dot dA, or we can add integration bada cos theta. The magnetic flux for a closed surface is always 0. So if it is closed surface, answer always will be 0. Now let's see its unit. Phi is B into A, magnetic field into area, B into A. Magnetic field, unit of magnetic field is Tesla. For area it is meter square. So Tesla meter square is the unit of magnetic flux. This Tesla into meter square is called Weber. So Weber is also the unit of magnetic flux. Now its dimensional formula. Dimensional formula of phi is dimensional formula of magnetic field. It is m1 t minus 2 a minus 1. We just derived this one. m1 t minus 2 a minus 1. And the dimensional formula of area, it is L2. So we'll get m1 L2 t minus 2 a minus 1. From this you can say this m1 L2 t minus 2 is a dimensional formula of work. So we can also say this is joule per ampere. Okay, one of the unit for magnetic flux other than Weber is joule per ampere. Line integral of magnetic field is integration B dot dl. Line integral of magnetic field is integration B dot dl. Line integration of electric field is integration E dot dl. So B dot dl, the formula is mu 0 sigma I according to Ampere's circuital rule. Let's see its unit. Magnetic field means Tesla, length means meter. So Tesla into meter is the unit of line integral of magnetic field. It's a dimensional formula. Dimensional formula will be, see what is the dimensional formula of magnetic field. See Tesla, the dimensional formula is m1 t minus 2 a minus 1 into meter means L1. So this will become m1 L1 t minus 2 a minus 1. Somewhere m1 L1 t minus 2 is a dimensional formula of force. So we can say this is force per ampere. Okay. Torsional constant is also called torque constant. Like imagine if this is suppose a spring, helical spring. In case of a helical spring, we have mass attached, and when it is oscillating, we can say the force acting on it is given by F is equal to minus ky. Okay. If you write down the magnitude, F is equal to plus ky. This is the force, linear force. This is linear displacement. This is constant. This constant is called force constant of a spring or a spring constant. But if you talk about a spiral spring, if you have seen in the old toys in which we were giving a rotational motion via a key, so in that case we have tau is equal to k phi. How? See, this is force. The in case of linear motion we have force. In case of rotational motion we have torque. In case of linear motion we have displacement. In case of rotational motion we have angular displacement. So if this is a force constant, this is called torque constant or torsional constant. So torsional constant basically is k is equal to t by phi. It's one more formula. See, tau is equal to bina. In case of galvanometer we have tau is equal to bina sin theta or just bina for galvanometer. So we can write k is equal to bina by phi also. Now let's see its unit. The unit of torque, see, k is a tau by phi. the unit of torque is Newton meter, and the unit of this angular displacement is radian. So Newton meter per radian. Its dimensional formula, as radian is supplementary quantity, its dimensional formula will be exactly as that of torque, that is Newton meter, that will be m1 L2 t minus 2. Okay, so this was all about torsional constant. Gyromagnetic ratio. Gyromagnetic ratio is actually the ratio of charge per unit mass twice the mass. E by 2m is called gyromagnetic ratio, and actually this comes from the ratio of magnetic moment and angular momentum of an electron. See, imagine suppose this is an atom, this is proton, neutron, and this is an electron. When the electron is revolving around the nucleus, see this electron, if it is moving like this in this direction, then due to the motion of negative charge in this direction, we can say a current will produce in this direction. This is the direction of current. Due to this current, somewhere some magnetic moment is produced. Why? Because current produces magnetic field, and due to that magnetic field a magnetic moment is produced. The magnetic moment for an atom is m is equal to INA mina. Here number of turns, there is no coil, this is just a single electron, therefore when the electron is moving it will have just a single coil like thing. So mi is equal to Ia. I is the current constituted due to the motion of electron, and that current is given by I is equal to Q by T into area. This charge is E, and that charge is passing in time capital T, so E by T into area is meter square. So magnetic moment is charge by time into meter square. And similarly angular momentum, see we have studied that Bohr's postulate in chapter number 12, that angular momentum is given by the formula L is equal to mvr is equal to nh by 2 pi. So when we take the ratio of these two, we have a shortcut, we get m by L. M means magnetic moment by angular momentum. This gives E by 2m. So the unit of this E by 2m will be, E is charge, is 1.6 into 10 to the minus 19, that is charge, by m is the mass of electron by kg. So coulomb per kg is the unit of gyromagnetic ratio. Its dimensional formula will be, see, coulomb per kg. Coulomb means A1 T1 by kg means M1. So this becomes M minus 1 T1 A1. So this is the dimensional formula of gyromagnetic ratio. Current sensitivity. Current sensitivity is defined as deflection in ammeter per unit electric current passing through it. Current sensitivity may be of galvanometer also. So imagine, suppose this is an ammeter. This is suppose 0 and this is suppose 10. Okay, if this is the pointer. Now the deflection, see, if current is 1 for 1 ampere of current, like if this is 1 ampere here, then this angle is phi and the current is 1 ampere. Okay, the deflection in galvanometer per unit electric current passing through it is called current sensitivity. So current sensitivity is phi by I. More it is sensitive, more it will show the deflection per unit current. Imagine suppose there is another ammeter which shows like this is 0 and which shows 1 ampere here. So we can say the angle in this case is greater, so the sensitivity of this galvanometer will be greater. So phi by I is the current sensitivity. The unit of phi is radian, current is ampere, so radian per ampere is the unit of current sensitivity. Its dimensional formula will be A minus 1. Other than this, we have a formula, phi by I is equal to bank, BAN by K. Okay, bank. Remember like this, BAN in numerator, K in denominator. So phi by I current sensitivity is given by the formula BAN by K. There is an NCERT numerical also on the base of this one. So phi is by I is BAN by K, where B is a magnetic field of the which is there inside the galvanometer. A is the area of the coil and are the number of turns of the coil, and K is the torsional constant of the coil we just discussed now. So next is voltage sensitivity. Voltage sensitivity Voltage sensitivity is defined as deflection per unit voltage. That will be radian per volt. This is the unit. It's a dimensional formula. We can write it is radian. Radian is unitless. We can say it is V minus 1, voltage minus 1. Voltage is work done per unit positive charge. So we can say this is charge per work. It's inverse of work done per unit positive charge. So I have written Q by V. Q is A1 T1. Work is M1 L1 T minus 2. Sorry, M1 L2 T minus 2. So the dimensional formula for voltage sensitivity becomes M minus 1 L minus 2 T3 A1. Okay, so this is the dimensional formula of voltage sensitivity. So here this is the end of chapter number 4.